Moving on to the next part of our discussion on simple circuits. Let's take a look at a couple of examples. We have examples part 1. So let's have the following problem. You have sample problem number 1. In the circuit shown, determine small r and capital R. We have two resistors, resistance small r and resistance capital R. The terminal voltage of the 12 volts EMF source, the terminal voltage is 11 volts. So the EMF of this EMF source, it has small resistance, it has internal resistance small r, meaning we have a real EMF source. The EMF rating of this EMF source is 12 volts. Whereas the terminal voltage, the voltage across the terminals of the real EMF source, V, is 11 volts. So V is equal to 11 volts, EMF is equal to 12 volts. The figures tells us that the current flowing through the circuit as shown is 6 amperes. So let I be equal to 6 amperes. We are looking for small r and capital R. We have a real EMF source. The equation for real EMF source we know to be V is equal to EMF plus minus IR. We know V, we know EMF, we know I. The only unknown is small r. We will be able to determine small r as soon as we determine what sign to use. Do we use plus sign or do we use the minus sign? For that, we take a look at the current I. What part of the EMF will the current enter? Will it enter the negative side or the positive side of the EMF source? So following the flow of the current, we see that the current will enter the negative side of the EMF. We use minus sign. So V is equal to EMF minus IR. Isolating R is equal to EMF minus V over I. We know EMF, we know V, and we know I. We are able to calculate the small resistance R, 0.167 ohms. So, small r is equal to 0.167 ohms. Now, the real EMF source is connected parallel to the resistance capital R, which means the voltage across the real EMF source is the same as the voltage across the resistor. The voltage across the EMF source, that's terminal voltage V. That means the terminal voltage V is also the voltage across the resistance, the resistor R. And Ohm's law tells us V is equal to IR. I is still 6 ohms. 6 ohms is the current flowing through the resistance R. Isolating R is equal to V over I. Thus, we are able to calculate the resistance capital R. R is equal to 1.833 ohms. Next, we have sample problem number 2. In the circuit shown, Determine the equivalent resistance of the network of resistors as well as the current passing through each resistor. So we have the following circuit. We have a 24 volts power source. Let that be V. V is equal to 24 volts. We have the following resistors. Let R1 be the 3 ohm resistor. R2 is the 4 ohm resistor. R3 is the 8 ohm resistor. R4 and R5 are the 6 ohm resistors. And the remaining resistor, the 5 ohm resistor, let that be R6. So we have R1, R2, R3, R4, R5, and R6. R2 and R3 are parallel with respect to each other. So we may combine these two resistors, these two resistances, using resistors in parallel connection. R2, R3, combining them into equivalent resistance R23, you have 1 over R23 plus 1 is equal to 1 over R2 plus 1 over R3. Knowing R2 and R3, we are able to determine R23. R23 is equal to 2.6666 and so on ohms. Likewise, R4 and R5 are parallel with respect to each other. So once again, using resistors in parallel connection, we combine R4 and R5 into equivalent resistance R4, 5. We have 1 over R4, 5 is equal to 1 over R4 plus 1 over R5. Knowing R4, knowing R5, we are able to determine R4, 5. R4, 5 is equal to 3 ohms. With R23 and R4, 5 determined, the resistances are now all in series connection. You have R1, R23, R4, 5, and R6. They are in series connection. We may combine the resistors in series connection to determine the equivalent resistance. R equivalent is equal to R1 plus R23 plus R4, 5 plus R6. Thus, we are able to determine the R equivalent. R equivalent is equal to 13.667 ohms. Now, R equivalent is parallel to the 12 volts power source, which means the voltage across R equivalent is also equal to 24 volts, equal to V. Ohm's law tells us, Ohm's law, V is equal to IR, V is equal to IR equivalent. Isolating R, we are able to calculate the total current I. 1.756097,561 amperes. Now, this total current I, that current I is passing through R1, passing through R23, passing through R45, and passing through R6. Resistors in series connection, which means R1, R23, R45, and R6 all have the same current. And that current is total current I. So, current through R1, I1, and current through R6, you have I6. I1 and I6 are both equal to total current I. I1 is equal to I6 is equal to 1.756 amperes. Now, current I is passing through resistance R23. So, Ohm's law tells us V23 is equal to I R23. We are able to determine the voltage V23, 4.68292683 volts. Resistors in parallel connection, V2 and V3, voltage across R2 and voltage across R3 are the same. They are both equal to V2, 3. Using Ohm's law on V2, V2 is equal to I2 R2. I2 is equal to V2 over R2. We know V2, we know R2, we are able to determine I2. 1.171 amperes. Similarly, for voltage V3, V3 is equal to I3R3. Isolating I3, I3 is V3 over R3. We know V3. We know R3. R3. We are able to determine I3. I3 is equal to 0.585 amperes. Current I is also passing through R45. Ohm's law tells us V45 is equal to I R45. We know I, we know R45. We are able to determine V45. 5.268292683 volts. R4 and R5 are in parallel connection, meaning they have the same voltage. V4 is equal to V5 equal to V4, 5. Resistors in parallel connection. Using Ohm's law on V45, V45 is equal to I4R4. Isolating I4, I4 is equal to V4 over R4. We know V4, we know R4, thus we are able to determine I4. 0.878048780 amperes. And since R5 is also 6 ohms, the same as R4, the current I5 is the same as current I4. I5 is also equal to 8.878048780 amperes. Thus, I4 is equal to I5 is equal to 0.878 amperes. And that's it for this video. That's it for now. That's it for our discussion on examples part 1. We'll continue our discussion in the next video. In fact, we will finish the topic of simple circuits in the next video. In the next video, we'll take a look at a couple of more examples. So again, that's it for now. Thank you for watching.